NASA just confirmed something that rewrites everything we thought we knew about life in our solar system. Beneath the icy surface of Ganymede, Jupiter's largest moon, there's an ocean. Not a puddle, not frozen water deposits. An actual ocean larger than all of Earth's surface water combined, hidden under miles of ice in the most hostile environment imaginable. And the implications are staggering. For decades, scientists suspected water might exist on distant moons. They had theories, models, mathematical predictions. But Ganymede was different from the start. When Galileo first spotted it in 1610 through his primitive telescope, he had no idea he was looking at what might be the most important body of water in the known universe. He just saw a bright dot orbiting Jupiter. For centuries later, we're staring at data that suggests this frozen world harbors more liquid water than our entire planet. The confirmation didn't come from a single observation. It emerged from years of meticulous detective work, analyzing magnetic fields, studying how Ganymede interacts with Jupiter's radiation, and piecing together clues that individually meant nothing but together painted an undeniable picture. The Hubble Space Telescope played a crucial role, not by taking pretty pictures, but by watching something most people would find utterly boring. Auroras. Ganymede has auroras, just like Earth. Shimmering lights dancing across its surface, generated by charged particles interacting with its magnetic field. But here's where it gets interesting. These auroras wobble. They rock back and forth in a specific pattern, and that pattern only makes sense if there's a massive conducting layer beneath the ice. Salt water conducts electricity. Ice doesn't. The math was unavoidable. Jupiter's magnetic field is brutal. It's the strongest planetary magnetic field in our solar system, roughly 20,000 times more powerful than Earth's. This field constantly batters Ganymede, which has its own magnetic field, the only moon in our solar system that does. When these two fields interact, they create observable effects on the surface. The auroras shift. They move. And by measuring exactly how they move, scientists could calculate what must be underneath. The ocean isn't sitting right below the surface. Ganymede's structure resembles a layered cake of ice and water. The outermost layer is solid ice, roughly 100 miles thick. Beneath that, liquid ocean. Below the ocean, another layer of ice. Then possibly another ocean. The entire structure extends down hundreds of miles, with the deepest ocean potentially sitting on a rocky seafloor rich in minerals. Temperature plays a bizarre role here. The surface of Ganymede hovers around -170 degrees Celsius. At that temperature, any exposed water would freeze solid in seconds. But deep beneath the ice, pressure and internal heat from tidal forces keep the water liquid. Jupiter's gravity squeezes and stretches Ganymede as it orbits, generating friction, creating warmth. Not enough to make the moon comfortable, but enough to maintain liquid water in the darkness below. The sheer volume is difficult to grasp. Earth's oceans contain roughly 1.335 billion cubic kilometers of water. Ganymede's subsurface ocean likely contains more. Some estimates suggest 2 to 3 times Earth's total water volume, all hidden beneath an alien ice shell, never touched by sunlight, existing in permanent darkness at pressures that would crush most submarines instantly. This discovery fundamentally changes the search for life beyond Earth. For years, the focus remained on Mars. Red dirt, ancient riverbeds, the possibility of microbial life clinging to existence in underground pockets. Mars made sense because it's close, relatively accessible, and clearly had water in its past. But Ganymede has water now. Liquid, stable, potentially rich in the chemistry needed for biology. Life on Earth exists in the strangest places. Deep ocean vents spewing superheated water create ecosystems thriving without sunlight. Microbes live miles underground in solid rock. Organisms survive in Antarctic lakes sealed beneath ice for millions of years. If life can adapt to those conditions here, why not in Ganymede's ocean? The ingredients are present. Water, energy from tidal heating, and potentially organic compounds delivered by ancient asteroid impacts. The history of this discovery stretches back further than most realize. The Voyager missions in the late 70s provided the first close-up images of Ganymede, revealing a surface unlike anything seen before. Strange grooves, impact craters, and regions of different ages suggested geological activity. Something was reshaping this moon's surface, but without plate tectonics or volcanic activity, the mechanism remained mysterious. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, gathered data that hinted at subsurface oceans on multiple moons. Its magnetometer detected induced magnetic fields around Ganymede, Europa, and Callisto, suggesting conducting layers beneath their surfaces. But the data was incomplete, subject to interpretation, and scientists remained cautious. Extraordinary claims require extraordinary evidence. That evidence accumulated slowly. Computer models improved. Understanding of tidal heating mechanisms deepened. Observations from Earth-based telescopes added pieces to the puzzle. The Hubble aurora measurements provided the breakthrough, offering indirect but compelling proof that couldn't be explained any other way. The scientific community reached consensus. Ganymede has an ocean. But knowing an ocean exists and understanding it are entirely different challenges. The ice shell separating this ocean from space presents an almost impenetrable barrier. 100 miles of solid ice. No drill bit created by human engineering could penetrate that thickness. Any mission to directly sample Ganymede's ocean requires technology that doesn't exist yet, solutions to problems we're only beginning to understand. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023. It won't arrive at Jupiter until 2031, then spend years studying Ganymede, Europa, and Callisto in unprecedented detail. JUICE carries instruments designed to peer through the ice, map the ocean's depth, analyze its composition, and search for signs of geological activity. It won't land, won't drill, won't sample the water directly. But it will transform our understanding. NASA's Europa Clipper, launching in 2024, focuses primarily on Europa, another Jovian moon with a subsurface ocean. But its findings will inform our understanding of Ganymede. These moons share similar characteristics, formed under comparable conditions, subjected to the same gravitational forces. Lessons learned from one apply to the others. The timeline frustrates everyone involved. Space missions take decades from conception to data collection. JUICE won't provide its most detailed Ganymede observations until the mid-2030s. Any follow-up mission to actually land on the surface and attempt to reach the ocean wouldn't launch until the 2040s at the earliest, possibly later. We're looking at a multi-generational project, where scientists designing today's missions may never see their ultimate conclusions. Yet the discovery itself, the confirmation that this ocean exists, represents a pivotal moment. For the first time in human history, we know with confidence that another world in our solar system harbors vast amounts of liquid water. Not ancient water, not frozen deposits that might melt someday. Water existing right now, potentially supporting ecosystems we can't yet imagine. The chemistry of Ganymede's ocean remains largely unknown. Is it fresh water or salt water? What minerals are dissolved in it? Are there organic compounds? Does the rocky seafloor host hydrothermal vents like those on Earth? Each question branches into dozens more, creating a web of mysteries that will occupy scientists for generations. Tidal heating provides the energy source, but how much energy? Earth's ocean vents support complex ecosystems because they pump out heat and chemicals continuously. If Ganymede's ocean floor has similar features, the energy budget might support life. If it's geologically dead, just cold dark water sitting motionless for billions of years, the prospects dim considerably. The multiple ice and water layers add complexity. Some models suggest up to 3 separate oceans stacked vertically, each isolated from the others by ice layers of different densities and crystalline structures. Communication between these layers would be minimal or non-existent. Life could potentially exist in one layer while others remain sterile. Or each layer might host distinct ecosystems adapted to specific conditions. Radiation presents another factor. Jupiter's magnetosphere traps high-energy particles that constantly bombard its moons. Ganymede's magnetic field provides some protection, but the surface still receives significant radiation doses. The ice layer shields the ocean from this radiation, but organic molecules on or near the surface would be quickly destroyed. Any life on Ganymede must exist deep, protected by miles of ice from the hostile radiation environment above. The philosophical implications ripple outward. If life exists in Ganymede's ocean, it would prove that biology isn't unique to Earth. The argument shifts from whether life exists elsewhere to how common it might be. If 2 bodies in one solar system both harbor life, the universe likely teems with it. Every star becomes a possibility, every planet and moon a potential incubator. But we're getting ahead of ourselves. Right now, we have confirmed water and plausible conditions. That's all. The leap from conditions to actual biology remains enormous, filled with uncertainties and assumptions. Life might be common, or Earth might be a cosmic fluke that won't repeat for billions of light years in any direction. What makes Ganymede particularly intriguing is its stability. Mars lost most of its water billions of years ago. Venus turned into a hellscape. Earth's oceans face eventual evaporation as the sun ages. But Ganymede's ocean, locked beneath protective ice and powered by tidal forces that will continue for billions of years, might be more stable than anything on Earth. If life took hold there, it could persist longer than life on our own planet. The size of Ganymede itself matters. At 5,268 kilometers in diameter, it's larger than Mercury, the smallest planet in our solar system. If Ganymede orbited the Sun instead of Jupiter, we'd classify it as a planet. Its substantial gravity holds onto a thin atmosphere, primarily oxygen produced when radiation splits water molecules on the icy surface. The oxygen immediately freezes or gets stripped away by Jupiter's magnetosphere, but its presence confirms water is being processed. Human exploration of Ganymede belongs to science fiction for now. The radiation alone makes crewed missions nearly impossible with current technology. Any spacecraft approaching Jupiter enters a radiation environment that would kill unprotected astronauts within hours. Shielding heavy enough to protect humans would make the spacecraft too massive to launch economically. Robotic missions remain our only viable option for the foreseeable future. That limitation doesn't diminish the significance. Robots can go where humans cannot, endure conditions we'd never survive, and operate for years without food, water, or breathable air. The Voyager probes, launched in 1977, still send data from interstellar space. Properly designed, a mission to Ganymede's ocean could operate for decades, slowly unraveling its mysteries. The technical challenges are staggering but not insurmountable. We need better power sources for long-duration missions far from the Sun where solar panels become useless. We need autonomous systems capable of making decisions without waiting for instructions from Earth, since radio signals take nearly an hour to travel between Jupiter and home. We need materials that can withstand extreme cold, high radiation, and the crushing pressures of deep ice. Engineers are already working on concepts. Nuclear-powered cryobots that could melt through ice. Autonomous submarines designed for alien oceans. Instruments sensitive enough to detect organic molecules in tiny water samples. Each component pushes the boundaries of current technology, but none require physics we don't understand. It's engineering, not magic. The cost will be enormous. A mission to land on Ganymede, drill through the ice, and explore the ocean would likely exceed $20 billion, possibly much more. That's a significant fraction of NASA's entire annual budget. International collaboration could spread the cost, but coordinating such a complex mission across multiple space agencies introduces its own challenges. Yet the alternative is remaining ignorant about what might be the most important discovery in human history. If life exists in Ganymede's ocean, finding it would answer humanity's oldest question. We are not alone. And if the ocean is sterile despite having the right conditions, that tells us something equally important about how rare and precious life might be. The next decade will lay the groundwork. JUICE and Europa Clipper will provide the detailed reconnaissance needed to plan future missions. They'll map the ice thickness, identify regions where it's thinnest, search for cracks or areas of geological activity where access might be easier. They'll measure the ocean's salinity, depth, and temperature as precisely as possible from orbit. Based on that data, space agencies will design the next generation of missions. Maybe a lander that can survive on the surface long enough to conduct detailed studies. Perhaps a penetrator that can punch through several miles of ice and deploy sensors. Possibly even a submarine, delivered through a borehole, that could explore the alien sea. Human curiosity demands answers. We've spent centuries wondering whether we're alone in the universe. Now we know where to look. Beneath the ice of a distant moon, in an ocean larger than all of Earth's seas combined, the answer might be waiting. The engineering challenges alone could fill textbooks. Ganymede's surface temperature hovers around -160 degrees Celsius. Electronics freeze. Lubricants solidify. Batteries lose efficiency. Every component must be designed to function in conditions that would instantly shut down equipment built for Earth. Then there's the ice itself. We're not talking about a frozen pond. The ice shell could be 50 miles thick in places. That's nearly 10 times the height of Mount Everest, except vertical and solid. Drilling through that much ice isn't a matter of bringing a bigger drill. The pressure increases with depth. The ice at the bottom behaves differently than the ice at the top, transitioning from brittle crystal to something more plastic, almost flowing under its own weight. A cryobot melting its way down would need to generate enormous heat continuously, requiring either a radioisotope thermoelectric generator or a compact nuclear reactor. The power source must be small enough to fit in a deployable probe yet robust enough to operate for months or years. It needs to survive radiation from Jupiter. It must avoid contaminating the very environment we're trying to study with Earth microbes that might hitchhike on the spacecraft. Planetary protection protocols will be stricter for Ganymede than for any previous mission. If there's even a possibility of indigenous life, we cannot risk introducing terrestrial organisms that might outcompete or contaminate native biology. Every surface must be sterilized. Every seal must be perfect. The probe becomes a self-contained bubble of Earth technology, isolated from the alien world it's trying to explore. Now add communication problems. A probe beneath miles of ice cannot send radio signals back to an orbiter. Ice blocks electromagnetic radiation effectively. This means either the probe must carry an extremely long cable, unreeling it as it descends, or it must operate completely autonomously, storing data until it can surface or relay information through the borehole. Autonomy introduces new complications. The probe needs artificial intelligence sophisticated enough to navigate unknown terrain, identify interesting features, avoid hazards, and make scientific decisions without human input. If it encounters something unexpected, it cannot phone home for instructions. Round-trip light time to Jupiter means waiting nearly 2 hours for a response to any question. In a dynamic environment, that delay could be fatal to the mission. Consider the submarine concept. Once through the ice, the vehicle must operate in total darkness under pressures that could reach several hundred atmospheres if the ocean is deep enough. It needs propulsion systems that work in extremely cold water. It requires sensors that can detect and analyze whatever might be floating in that alien sea, from simple organic molecules to potential life forms. What happens if the submarine encounters something alive? The protocol must be designed in advance. Does it collect samples? Does it observe without touching? How do you balance scientific curiosity with the ethical implications of disturbing an alien ecosystem that has existed in isolation for billions of years? These aren't abstract philosophical questions. Mission designers must answer them before launch because there's no opportunity to revise the plan once the spacecraft leaves Earth. Every contingency must be anticipated. Every failure mode must have a backup. Space exploration runs on redundancy and careful planning, not improvisation. The timeline stretches across decades. JUICE launched in 2023 and won't arrive at Jupiter until 2031. Europa Clipper launches in 2024 with arrival in 2030. Both spacecraft will spend years conducting flybys, gathering data, refining our understanding. Based on their findings, a lander mission might launch in the late 2030s, arriving in the mid-2040s. A drilling mission could follow in the 2050s. A submarine exploring the subsurface ocean might not splash down until the 2060s or later. This assumes steady funding, no major technical setbacks, and sustained political will across multiple administrations and international partnerships. Space missions operate on timescales that outlast careers, sometimes outlast entire space agency strategic priorities. The people who design these missions often retire before launch. The scientists who propose investigations might not live to see the results. Yet the work continues because the questions matter. Does life exist elsewhere? Is Earth unique, or is biology a common outcome when the right conditions persist long enough? Ganymede offers a test case. It has liquid water, energy sources, and complex chemistry in a stable environment that has existed for billions of years. If life can arise and persist there, it suggests the universe might be teeming with biology in places we never thought to look. The alternative is equally profound. If Ganymede's ocean is sterile despite having everything life needs, that implies something about Earth's biosphere is special, rare, perhaps unique. It means the origin of life requires more than just the right ingredients. It suggests we might be alone after all, or at least that living worlds are far more scarce than optimistic estimates predict. Scientists debate these possibilities constantly. Some argue life is inevitable given the right conditions, that chemistry naturally progresses toward biology, that the universe should be full of microbes at minimum. Others counter that Earth's biosphere might depend on a precise sequence of unlikely events, that life requires not just water and energy but specific catalysts, particular mineral surfaces, or rare chemical pathways that don't exist everywhere. Ganymede will provide evidence, not proof, because proving life doesn't exist anywhere is impossible. You can only prove it does exist by finding it. But if we search thoroughly and find nothing, that shifts the probabilities. It means life is either rarer than we hoped or hidden in ways we don't yet understand. The search itself will advance technology in unexpected ways. Developing autonomous systems for Ganymede will improve robotics here on Earth. Materials that can withstand Jupiter's radiation environment will find applications in nuclear facilities and medical equipment. Power systems designed for deep space will influence energy technology for remote terrestrial locations. Space exploration has always produced spin-off benefits far beyond its primary objectives. But those practical applications aren't why we go. We go because not knowing is intolerable. Humans don't look at locked doors and walk away satisfied. We pick the lock, we break it down, we find another entrance. Ganymede is a locked room the size of a planet, and we've just started examining the hinges. The ocean might be vast and empty, devoid of anything more interesting than water and dissolved salts. That would be disappointing but still valuable. We'd learn about oceanography in low-gravity environments. We'd understand how heat flows through icy moons. We'd gather data about chemistry in sealed systems isolated for geological timescales. Or we might find something that changes everything. Not necessarily intelligent life. Even single-celled organisms would be revolutionary. Bacteria, if we can call them that, adapted to crushing darkness and extreme cold. Microbes that derive energy from chemical gradients rather than sunlight. Simple life following different biochemical rules, using different molecules, perhaps not even based on DNA. That last possibility excites biologists especially. All life on Earth uses the same genetic code, the same basic molecular machinery. We're all related, descended from a common ancestor that lived billions of years ago. But if life arose independently on Ganymede, it might have found different solutions to the same problems. Different information storage molecules. Different energy currencies. Different ways of building cells and regulating metabolism. Comparing Earth life to Ganymede life, if it exists, would reveal which aspects of biology are universal and which are accidents of history. It would show us what life must do to exist versus what Earth life happens to do because that's how it evolved here. That knowledge would transform biology from a historical science describing what happened on one planet to a predictive science explaining what must happen anywhere. The implications extend beyond pure research. Understanding life's minimal requirements would guide searches for habitable planets around other stars. It would inform discussions about terraforming, about creating conditions for life in places currently sterile. It might even reveal new approaches to biotechnology, new ways of engineering organisms or synthesizing useful compounds. But these practical considerations fade next to the fundamental question. In 4.5 billion years of Earth's history, in hundreds of millions of species that have lived and died, in all the complexity of the biosphere from bacteria to blue whales, has life happened only once? Or is it happening right now, independently, in a dark ocean beneath the ice of a distant moon? We're close to finding out. Not tomorrow. Not next year. But within the lifetime of people alive today, we will send machines to Ganymede capable of answering that question. They'll drill through the ice, sample the water, analyze what they find with instruments sensitive enough to detect organic molecules at concentrations of parts per billion. If those instruments find nothing, we'll build better ones. We'll look in different locations. We'll develop new techniques. The absence of evidence doesn't mean evidence of absence, especially when searching an ocean millions of cubic kilometers in volume. But if we find something, anything that moves on its own, that consumes energy, that reproduces, that fits any reasonable definition of life, then we'll know. Human beings will have discovered that we are not alone in the universe. That life exists beyond Earth. That the cosmos is not a sterile void punctuated by one lonely living world, but a place where biology emerges wherever conditions allow. And if a frozen moon of Jupiter hosts life, what about the hundreds of billions of other planets and moons in our galaxy alone? The discovery wouldn't happen all at once. There'd be no single dramatic moment when a scientist points at a screen and shouts that we found aliens. Instead, it would unfold through careful analysis, repeated tests, heated debates in conference rooms and academic journals. Someone would notice unusual chemical signatures in return samples. Organic molecules with strange isotope ratios. Compounds that seem too complex to form through simple chemistry. The first papers would be cautious, hedging their conclusions, suggesting that further investigation is warranted. Then other teams would examine the same data and reach similar conclusions. The evidence would accumulate slowly. Lipid-like molecules that could form membranes. Polymers that might store information. Traces of metabolic processes that can't be explained by known geological chemistry. At some point, the weight of evidence would become overwhelming. The scientific consensus would shift from skepticism to acceptance. But convincing the broader world would take longer. News media would sensationalize the findings, alternating between wild speculation and dismissive skepticism. Social media would erupt with conspiracy theories. Religious leaders would grapple with theological implications. Philosophers would debate what it means for humanity's place in the cosmos. Politicians would argue about funding priorities and international cooperation. Meanwhile, scientists would already be planning return missions. Not just sample return this time, but direct observation. Submersibles that can swim through Ganymede's ocean for months or years, equipped with cameras and sensors and AI systems sophisticated enough to recognize life when they see it. Because finding evidence of life and actually observing living organisms are two very different achievements. Consider what those organisms might look like. On Earth, life in similar environments, deep ocean hydrothermal vents shrouded in permanent darkness, has evolved into bizarre forms. Tube worms 3 meters long with no mouth, no digestive system, surviving on bacteria that live in their tissues. Eyeless shrimp clustering around volcanic vents, their backs covered in light-sensitive organs that detect the faint infrared glow of superheated water. Fish with enormous mouths and bioluminescent lures, adapted to a world where food is scarce and every meal counts. Ganymede's life would face similar pressures but with crucial differences. Earth's deep ocean is connected to the surface. Organic matter drifts down from the sunlit zones above. Dead plankton, fish carcasses, even whale falls that sustain entire ecosystems for decades. Ganymede's ocean has no such connection. No photosynthesis occurring anywhere in the system. No rain of organic carbon from above. Everything must derive from chemistry. From the reactions occurring where water meets rock, where minerals dissolve and precipitate, where temperature and pressure create gradients that life can exploit. This means Ganymede's biosphere, if it exists, would be fundamentally limited in a way Earth's is not. The total amount of chemical energy available sets a hard ceiling on how much life can exist. On Earth, photosynthesis captures roughly 100 terawatts of solar energy. That's the foundation supporting everything else, from bacteria to humans. Ganymede's chemical energy budget would be orders of magnitude smaller. Maybe a few gigawatts at most, possibly much less. This has profound implications for what kind of life could exist there. Forget anything large or complex. No fish swimming through the darkness. No predators hunting prey. The energy simply isn't there to support such lifestyles. Instead, we'd expect to find microbial communities clustered around hydrothermal vents and chemical gradients. Perhaps biofilms coating rock surfaces, slowly metabolizing minerals. Maybe free-floating cells drifting through the ocean, living at such a slow pace that their metabolism would be barely detectable. These organisms would likely reproduce slowly, grow slowly, evolve slowly. Where Earth bacteria can double in number every 20 minutes under ideal conditions, Ganymede microbes might take days or weeks. Their generation times could be measured in years. Evolution on Ganymede might proceed at a glacial pace compared to Earth, simply because there's less energy available to power the biochemical processes that drive mutation and selection. Yet that slowness wouldn't make them any less alive. They'd still be consuming energy, maintaining themselves against entropy, reproducing, evolving. They'd still represent an independent origin of life, a second example of biology emerging in the universe. And studying them would be incredibly difficult precisely because of that slow pace. Detecting metabolism when it happens over weeks instead of hours requires patience and sensitive instruments. Distinguishing living processes from chemical reactions becomes harder when both occur at similar speeds. Proving that something reproduces when reproduction takes months to complete means waiting months between observations. Traditional microbiological techniques developed for Earth organisms, techniques that rely on culturing bacteria in labs and watching them grow, might not work at all. We'd need entirely new approaches. Genetic sequencing, if Ganymede life uses anything resembling DNA or RNA. Chemical analysis of cell components. Microscopic observation of cellular structures. Isotope tracing to track the flow of elements through metabolic pathways. Each technique would have to be adapted for organisms that might not resemble Earth life in any obvious way. And there's a darker possibility worth considering. What if we contaminate Ganymede's ocean before we even realize it harbors life? Every spacecraft we send carries Earth microbes, despite our best sterilization efforts. Some bacteria can survive the vacuum of space, survive intense radiation, survive years of dormancy. If even a few cells reach Ganymede's ocean, they might find conditions suitable for growth. Earth microbes, adapted to environments with abundant energy, might outcompete native Ganymede organisms in the same way invasive species devastate island ecosystems on Earth. We could destroy an entire alien biosphere before we even confirm it exists. This is why planetary protection protocols are so important, why we heat-sterilize spacecraft components, why we plan trajectories that avoid impacting potentially habitable worlds. But protocols aren't perfect. Accidents happen. Missions fail. A spacecraft could crash on Ganymede's surface, its fragments eventually working their way through cracks in the ice to the ocean below. Or perhaps contamination has already occurred through some path we haven't anticipated. Natural processes, for instance. Meteorite impacts eject material from planetary surfaces into space. Rocks from Mars have landed on Earth. Rocks from Earth might have reached Ganymede over the solar system's history. If Earth microbes arrived on Ganymede millions of years ago, encased in rock from an impact event, could they have survived? Could they have adapted to the conditions there? This raises an unsettling question. If we find life on Ganymede, how do we prove it originated there independently rather than being related to Earth life that contaminated the Moon long ago? The answer lies in biochemistry. If Ganymede organisms use the same genetic code as Earth life, the same amino acids, the same basic molecular machinery, that would suggest a common origin. Either contamination or panspermia, the idea that life spreads between worlds on meteorites. But if Ganymede life uses different molecules, different information storage systems, different metabolic pathways with no clear connection to Earth biochemistry, that would prove independent origin. Testing this requires bringing samples back to Earth, analyzing them in laboratories with equipment too sophisticated to send to Ganymede. Which creates another problem. How do we safely return samples that might contain alien microbes? What if those microbes, despite evolving in a completely different environment, turn out to be dangerous to Earth life? The risk is probably minimal. Organisms adapted to Ganymede's high-pressure, low-energy environment likely couldn't survive in Earth's oxygen-rich atmosphere at normal pressure. They'd be as out of place here as we would be there. But probably isn't the same as certainly. So any sample return mission would require extraordinary precautions. Sealed containment from the moment samples are collected. Analysis in high-security biosafety facilities. Protocols for sterilization if anything goes wrong. We've done this before, actually. Apollo astronauts returning from the Moon were quarantined in case they brought back lunar pathogens. We now know the Moon is sterile, but the precaution was reasonable given what we knew then. Samples from Ganymede would require similar or greater care, because unlike the Moon, Ganymede actually might harbor life. These practical challenges, the engineering problems and safety protocols and mission designs, can make the search for life seem like a purely technical exercise. Build the right instruments, follow the right procedures, analyze the data correctly. But beneath the technical details lies something more profound. We're attempting to answer a question humans have asked since we first looked up at the night sky. Are we alone? For most of history, that question was purely philosophical. We could speculate, imagine, tell stories about other worlds and other beings. But we couldn't actually investigate. We couldn't go looking. Now we can. Not easily. Not quickly. But we have the technology and the knowledge to send machines to distant worlds in search for life. Ganymede represents our best near-term opportunity. Not the only one. Mars might harbor life in subsurface aquifers. Enceladus, another moon of Saturn, has a similar subsurface ocean that might be even more accessible than Ganymede's. Titan has liquid methane seas and complex organic chemistry. Each world offers a different chance to find biology beyond Earth. But Ganymede stands out because of what we already know about it. The ocean is definitely there. It's in contact with rock. It's existed for billions of years. The conditions, while extreme by Earth standards, fall within the range that could potentially support life. We're not guessing, we're hoping. We're investigating a real possibility based on solid evidence. That investigation requires missions that don't exist yet. We have orbiters studying Jupiter's moons from a distance. We have plans for future missions with more sophisticated instruments. But actually landing on Ganymede, drilling through kilometers of ice, reaching the ocean below, that's beyond our current capabilities. Not impossible. Just difficult and expensive and years away from being technically ready. Which means the search for life on Ganymede exists in a strange state. We know enough to make it compelling. Not enough to actually do it. We're caught between possibility and practicality, between what we want to know and what we can currently achieve. Consider what a Ganymede lander would need to accomplish. First, survive the journey. Jupiter's radiation environment is brutal. Electronics that work fine on Earth or even Mars would fail within hours near Jupiter without heavy shielding. The lander needs protection, but protection adds mass, and mass makes landing harder. Then there's the landing itself. Ganymede's surface is ancient ice, hard as rock, covered with craters and ridges and fracture systems. Finding a safe landing site requires detailed mapping. Avoiding hazards requires precision navigation. All while operating with a communication delay that makes real-time control from Earth impossible. Signals take merely an hour to travel between Jupiter and Earth at light speed. Commands sent now won't arrive for 43 minutes. Responses take another 43 minutes to return. Any crisis must be handled autonomously by the spacecraft itself. After landing comes the real challenge. Drilling. Not through a few meters of ice, but potentially kilometers. Earth has drilled through ice sheets in Antarctica and Greenland, reaching depths of several kilometers. But those drills are powered by massive equipment, operated by teams of engineers, supported by supply chains bringing fuel and replacement parts. A Ganymede drill would have none of that. It would need to be compact enough to fit on a spacecraft, light enough to launch from Earth, powerful enough to penetrate kilometers of ice harder than concrete, reliable enough to work without maintenance in an environment where the average temperature sits at -160 degrees Celsius. Some designs propose using heat to melt through the ice rather than mechanical drilling. A heated probe slowly descends, melting ice above it which refreezes after it passes, sealing the hole. This approach is elegant and potentially more reliable than mechanical systems. But it's also slow. Estimates suggest it could take years to reach significant depths. Years during which the probe must continue functioning, powered by a nuclear battery that slowly loses strength as its radioactive fuel decays. Other approaches use a combination of heating and mechanical drilling, or cryobots that navigate through existing cracks rather than drilling new holes, or autonomous submarines deployed through access points where ice is thinner, perhaps near the dark terrain where the ocean might be closer to the surface. Each approach has advantages. Each faces enormous engineering challenges. None have been tested in conditions resembling Ganymede's actual environment. We're not talking about adapting existing technology. We're talking about inventing new systems for problems we've never encountered. And we need those systems to work the first time, because there won't be a second chance to retrieve a probe that gets stuck halfway through an ice sheet 300 million kilometers from Earth. Assuming we solve the drilling problem, assuming we reach the ocean, what happens next? The probe needs to function underwater in conditions nothing from Earth was designed for. Pressure at the ocean floor could exceed 2,000 times Earth's surface pressure. Salt water with unknown chemistry might corrode materials in unexpected ways. The complete absence of light means any instruments must bring their own illumination. Swimming or moving along the bottom requires propulsion systems that work in dense, cold liquid under crushing pressure. Sampling the water, analyzing it for chemical signatures or biological material, transmitting results back to the surface through kilometers of ice and then across space to Earth. Every step presents technical obstacles. But suppose we overcome them. Suppose a probe successfully lands, drills through the ice, reaches the ocean, begins exploring. What would it actually look for? Life, if it exists in Ganymede's ocean, might not be obvious. It wouldn't be fish swimming past the camera or alien whales breaching near the probe. It would most likely be microbial. Single-celled organisms, possibly forming communities like the microbial mats found near Earth's hydrothermal vents, but nothing large or complex enough to see with a camera. Detection would rely on chemistry, looking for organic molecules that shouldn't exist without biological processes. Measuring ratios of chemical isotopes that indicate metabolic activity. Searching for patterns in molecular structure that suggest evolutionary optimization rather than random chemical reactions. On Earth, we can distinguish biological from non-biological processes with high confidence because we understand Earth biochemistry thoroughly. We know what molecules life uses, how they're structured, what isotope ratios result from different metabolic pathways. Ganymede life, if it exists, might work completely differently. It might use molecules we'd never associate with biology. It might produce isotope ratios that look random to us but actually represent alien metabolism. We might find clear evidence of life and not recognize it because we're looking for Earth patterns in an alien system. Or we might find ambiguous results. Organic molecules that could be biological or could be from non-biological chemistry. Isotope ratios that suggest metabolism or could result from geological processes. Energy gradients that look like they're being exploited by life or might just be natural chemical reactions finding equilibrium. The Viking landers on Mars in the 1970s faced exactly this problem. They conducted experiments designed to detect Martian microbes. Some results looked positive. Others were inconclusive. Decades later, scientists still debate whether Viking detected life or just unusual chemistry. A similar situation on Ganymede would be frustrating. We'd have invested billions of dollars and decades of work to reach a moon of Jupiter, drill through its ice, sample its ocean, and come back with results that don't definitively answer the question we went there to investigate. But even ambiguous results would be valuable. They'd tell us something about Ganymede's ocean chemistry. They'd reveal whether organic molecules exist there and in what concentrations. They'd help us understand the energy available for potential life and whether chemical conditions could actually support biology. Negative results would also matter. If we thoroughly sampled Ganymede's ocean and found no evidence of life, no organic molecules, no chemical signature suggesting biology, that would itself be significant. It would suggest that even with liquid water, the right chemistry, and billions of years, life doesn't automatically emerge. It would imply that life requires conditions beyond just liquid water and chemical building blocks. That the jump from chemistry to biology requires something special we don't yet understand. Which brings us back to the fundamental question driving this entire investigation. How does life begin? We know it happened at least once, on Earth, roughly 4 billion years ago. We don't know if it was inevitable or fantastically unlikely. We don't know if it requires specific conditions that are rare in the universe or if it emerges readily wherever basic requirements are met. Finding life on Ganymede would suggest it's relatively common. Two independent origins in the same solar system would imply life emerges frequently throughout the universe. Not finding life on Ganymede, especially after thorough searching, would suggest it's rare. That Earth might be unusual or even unique among the countless worlds in our galaxy. Both answers would be profound. Both would reshape how we understand our place in the universe. But one answer requires us to actually go there and look. Not just theorize or speculate based on distant observations. We need direct investigation. Ganymede challenges us in ways that push against our current technical limits. The radiation environment around Jupiter. The extreme cold. The massive ice shell. The crushing pressures in the deep ocean. Each obstacle has solutions, but implementing those solutions in a single integrated mission that actually works requires innovation and resources and time. Multiple space agencies have proposed concepts. Europa Clipper, launching soon, will study Jupiter's moons including Ganymede, gathering data that will help plan future missions. JUICE, the Jupiter Icy Moons Explorer, will orbit Ganymede directly, mapping its surface and ice shell in unprecedented detail. These are reconnaissance missions. They'll tell us where to look. They won't answer whether life is actually there. That requires landing. That requires drilling. That requires direct sampling. The earliest realistic timelines put such a mission in the 2040 period. Possibly later depending on funding and technical development. Which means if you're watching this now, the answer to whether life exists on Ganymede might not come in your lifetime. Or it might come tomorrow if we get extraordinarily lucky with existing data. Science operates on timescales that don't align with human patience. We want answers now. The universe provides them when it's ready, following its own schedule that doesn't care about our curiosity or our lifespans. Yet we keep looking. We keep planning missions and developing technology and training scientists who will analyze data from instruments that don't exist yet, studying a world most people will never even see clearly except in images taken by robots we send across the solar system. The search continues because some questions demand answers regardless of how difficult finding them might be. Maybe the answer isn't hiding in some distant ocean after all. Maybe we're approaching this entire question from the wrong angle, fixating on complexity when the real story is far stranger. Because there's another possibility we haven't fully confronted. Life might not be limited to places like Earth or Ganymede. It might exist in forms and locations so fundamentally different from what we know that we wouldn't recognize it even if we were looking directly at it. Consider Titan, Saturn's largest moon. It has lakes and rivers and rain, a complete hydrological cycle just like Earth. Except the liquid isn't water. It's methane and ethane, hydrocarbons flowing across a world where the surface temperature sits at -179 degrees Celsius. Chemistry at those temperatures operates under completely different rules. Reactions that happen instantly on Earth take geological timescales on Titan. Molecules that are gases here are liquids there. And yet Titan's atmosphere shows chemical imbalances that don't make sense without some active process continuously producing certain compounds. Something is consuming hydrogen at the surface. Something is depleting acetylene. The measurements are real. The interpretations are contested. Could be geological. Could be atmospheric chemistry we don't understand. Could be life, but life's so alien it doesn't resemble anything in our experience. Imagine organisms that use liquid methane instead of water as a solvent. That builds cell membranes from compounds stable at cryogenic temperatures. That metabolize in slow motion across timescales measured in Earth years rather than seconds. Would we even recognize their biochemistry as life? Our definitions are built around Earth biology. Carbon chains in water. DNA and RNA. Proteins folded in specific configurations. Energy from breaking chemical bonds in particular ways. Strip away those specifics and what's left? What's the irreducible core that separates living systems from complex chemistry? Self-replication, maybe. The ability to make copies. But crystals do that and we don't call them alive. Metabolism, extracting energy from the environment. But fire does that. Response to stimuli. Lots of chemical systems respond to their surroundings without being alive. The technical definition usually involves all of these together plus evolution, the capacity to change over generations through variation and selection. Yet even that gets murky at the edges. Viruses evolve but exist in a gray zone between chemistry and biology. Prion replicate and cause harm but contain no genetic material at all. We might be searching for Earth life in other locations when the universe has invented entirely different solutions to the same fundamental problem. How to persist. How to make order in a universe that tends toward disorder. How to harness energy flows to maintain complexity. Saturn's moon Enceladus shoots geysers of water into space from an underground ocean. The Cassini spacecraft flew through those plumes and detected organic molecules, salts, silica particles. Everything you'd expect from hydrothermal activity on an ocean floor. Almost identical to environments on Earth where life thrives around deep sea vents. But Enceladus is tiny. Its ocean might be only 10 kilometers deep. The entire moon is barely 500 kilometers across. Could something that small sustain life for billions of years? Does it matter? If life exists there, it exists. Size is a human concern. Biology doesn't care about our intuitions regarding what's possible. Venus presents a different kind of puzzle. The surface is hellish, hot enough to melt lead, pressure crushing enough to destroy spacecraft within hours. But 50 kilometers up in the atmosphere, conditions are surprisingly mild. Temperature and pressure similar to Earth's surface. Sulfuric acid clouds, yes, but microbes on Earth survive in acid. Thrive in it, even. And there's this persistent mystery in Venus's atmosphere. Phosphine, a gas that on Earth is only produced by life or human industrial processes. The detection has been challenged, reanalyzed, debated intensely. Maybe it's there, maybe it's not, maybe the instruments were misread. But if it is there, if it's real, then something is producing it. Life floating in the clouds of Venus would be genuinely alien, organisms that never touch solid ground, reproducing in droplets of sulfuric acid, cycling through the atmosphere for their entire existence. These scenarios push against our assumptions. We think of life as something that happens on surfaces, in oceans, in contact with rock. But why? Because that's how it works here. The universe might not care about our provincial expectations. And then there are the truly strange possibilities. Worlds where ammonia replaces water. Planets with silicon-based chemistry instead of carbon. Environments where life operates at temperatures near absolute zero or in the nuclear furnaces of stellar cores. Pure speculation, sure, but speculation constrained by physics and chemistry, not fantasy. The point isn't that any specific scenario is likely. The point is we don't know the boundaries of what's possible. Every time we think we've found life's limits, something on Earth survives in a place we thought was sterile. Microbes in nuclear reactor cooling pools. Organisms in subglacial lakes isolated for millions of years. Life in the driest deserts, the deepest ocean trenches, inside solid rock kilometers below the surface. Earth life adapted to those places, evolved to tolerate extremes. But what if life started in extremes elsewhere? What if the universe is full of biology that would find Earth hostile and bizarre, organisms for whom our comfortable temperatures and abundant water are toxic? Finding any form of life beyond Earth would be revolutionary. Finding life radically different from our own would be even more so. It would prove life isn't a single solution but a category of solutions. That the universe experiments with multiple approaches to the same fundamental challenge. The search has to account for this uncertainty. We can't only look for Earth twins. We need strategies for detecting life we don't recognize, biosignatures we haven't imagined. Which is extraordinarily difficult because you can't search for something when you don't know what you're searching for. Atmospheric chemistry offers one approach. Life, any life, has to exchange matter and energy with its environment. Those exchanges leave traces, chemical imbalances that persist because something is actively maintaining them. Oxygen in Earth's atmosphere is a biosignature because without life constantly producing it, oxygen would react away. It's chemically unstable over geological time. Other worlds might have different biosignatures. Gases that shouldn't coexist found together. Ratios of isotopes that don't match non-biological processes. Seasonal variations in atmospheric composition that suggest biological cycles. We can look for patterns without knowing exactly what's causing them. But that requires getting close enough to analyze atmospheres in detail. For planets around other stars, that means next-generation space telescopes powerful enough to separate a planet's light from its star's glare and break that light into spectra revealing chemical composition. The technology exists. The telescopes are being built. Within a decade, we'll have the capability to study potentially habitable exoplanet atmospheres. And then what? We detect oxygen and methane together on a world 30 light-years away. Strong suggestion of life, not proof. Could be geological, some process we don't understand producing those gases without biology. We'll debate it, analyze it, propose follow-up observations. But we won't know for certain. Not the way we'd know if we could land and look directly. The frustrating truth is certainty might be impossible for life beyond our solar system. We could find compelling evidence, strong suggestions, patterns that look biological. Absolute proof would require sending probes to other star systems, missions that would take thousands of years with current technology. Or developing fundamentally new propulsion methods, which might happen eventually but not soon. So we're left with probabilities and indirect evidence and scientific arguments that won't satisfy everyone. Which is fine, actually. Science doesn't require certainty to make progress. It requires better questions and methods for answering them. Within our solar system, we can achieve certainty. We can send robots to drill and sample and analyze with instruments sophisticated enough to detect life if it's there. Mars, Europa, Enceladus, Titan, Ganymede. Each world gets us closer to answering whether life is common or rare, whether Earth is typical or exceptional. And maybe the answer is both. Maybe simple life, microbes, basic cells, emerges readily throughout the universe wherever conditions permit. But complex life, multicellular organisms, intelligence, remains vanishingly rare. That would explain why we see no obvious signs of technological civilizations despite billions of habitable planets in our galaxy. Or maybe we're alone. Maybe life requires such a specific sequence of unlikely events that Earth is genuinely unique. For billion years of evolution on the only living world in the observable universe. That possibility terrifies some people. The cosmic loneliness of it. Personally, it seems no more lonely than the alternative. If life is everywhere, we're still separated by distances that make communication nearly impossible. If life is rare, at least we're special. Both scenarios leave us fundamentally isolated in a vast universe, responsible for preserving the only consciousness we know exists. The search continues not because we expect easy answers but because not searching would be worse. Accepting ignorance when knowledge is possible. Living with questions we could answer if we tried. That's not how humans operate. We're curious to the point of obsession, willing to spend decades and billions pursuing answers to questions most people never think about. And perhaps that obsession is itself evidence of something profound. The fact that we care about questions with no immediate practical benefit. That will dedicate careers to understanding whether microbes exist beneath Martian ice. That we build telescopes to analyze the atmospheres of worlds we'll never visit. This curiosity might be the most distinctively human trait we possess, more defining than tool use or language or social organization. Other intelligent species, if they exist, might not share it. They could be perfectly content within their own worlds, never wondering what lies beyond. Evolution doesn't guarantee curiosity. It guarantees survival strategies, and sometimes curiosity helps survival by driving exploration and innovation. But it's not inevitable. We could have evolved to be incurious, satisfied, uninterested in questions beyond immediate needs. We didn't. Something in the particular path human evolution took produced minds that can't stop asking why. Minds that see a star and wonder what it's made of. That find a fossil and reconstruct entire extinct ecosystems. That detect a chemical signature on a distant moon and immediately start planning missions to investigate. This compulsion has costs. Resources spent on space exploration could address immediate terrestrial problems. The billions invested in Mars rovers don't feed hungry people or cure diseases or solve climate change. Critics make this argument constantly, and it's not entirely wrong. Priorities matter. But the assumption that we must choose between cosmic exploration and earthly welfare creates a false dichotomy. Human civilization is wealthy enough to pursue multiple goals simultaneously. The amount spent on space science represents a tiny fraction of global economic activity. NASA's entire annual budget is less than what's spent on pet food in the United States. We're not choosing between feeding people and exploring Mars. We're choosing between various forms of discretionary spending, and some of that spending generates knowledge rather than consumption. Knowledge has value beyond immediate application. Understanding how planets form helps us understand our own planet's history. Studying extreme environments on other worlds informs our understanding of life's limits. Developing technology for space missions produces innovations that find terrestrial applications. GPS, weather forecasting, communications satellites, medical imaging techniques, all emerged from space programs. But even without practical spin-offs, the knowledge itself matters. Knowing whether we're alone in the universe changes how we think about existence, meaning, our place in reality. It's the kind of knowledge that shifts perspective, that makes us see ourselves differently. And that has value even if it doesn't produce marketable products. The search for life also forces us to confront uncomfortable possibilities about our own future. If we find dead worlds that once had life, worlds where biological activity left traces before going extinct, that tells us something about planetary evolution. Life emerges, thrives for a while, then disappears. Not a comforting pattern. Mars might be such a world. Early in its history, warmer, wetter, potentially habitable. Then it lost its magnetic field, its atmosphere stripped away by solar wind, surface water evaporating or freezing, whatever life existed either dying or retreating underground. A world that had its chance and lost it. Earth could follow the same trajectory. Not tomorrow, not in human timescales, but eventually. Our sun is gradually brightening, increasing energy output as it ages. In 1 billion years, maybe less, Earth's oceans will boil away. The planet will transition from habitable to sterile, life's 4 billion year run ending not with catastrophe but with slow inexorable change. Unless life spreads beyond Earth first. Unless consciousness finds ways to persist across multiple worlds, backing itself up against planetary disasters. This is one argument for space exploration that transcends curiosity. Survival of life itself as a phenomenon, as a process, as the universe's method for organizing matter into increasingly complex patterns. We're the only species capable of deliberately spreading life to other worlds. Every other organism is confined to Earth, dependent on this single planet's continued habitability. We have the technology to change that. Not easily, not soon, but possible within foreseeable futures. Establishing self-sustaining colonies on Mars or in orbital habitats or on moons throughout the solar system. Whether we should do this is a separate question. Planetary protection protocols exist specifically to prevent contaminating other worlds with Earth life before we've had a chance to study them in pristine condition. If Mars has indigenous life, even just microbes, introducing Earth organisms could destroy or outcompete them before we discover they exist. But if Mars is dead, if Europa and Enceladus contain only chemistry without biology, if we're genuinely alone in this solar system, then spreading life becomes not contamination but continuation. Taking the process that started on Earth and extending it outward, giving it redundancy, ensuring that life in general isn't dependent on one planet's survival. This assumes life has value, that preserving and spreading it matters. Not everyone accepts that premise. From a purely physical perspective, life is just complex chemistry. The universe doesn't care whether organized matter continues existing or breaks down into simpler forms. Stars will keep burning, galaxies will keep rotating, the cosmos will expand regardless of whether life persists anywhere. Yet we care. Consciousness cares about its own continuation. We value existence over non-existence, complexity over simplicity, preservation over destruction. These preferences aren't logically necessary. They're built into us by evolution because organisms that don't prioritize survival don't leave descendants. But the fact that our values are evolutionary products doesn't make them meaningless. We're parts of the universe that have become aware of themselves. Matter organized in specific ways that allow reflection, contemplation, understanding. The universe experiencing itself through consciousness. Poetic language, but also accurate description of what's happening when human brains process information about reality. If consciousness is rare, if Earth represents the only location in vast cosmic volumes where this self-awareness exists, then its preservation becomes critically important. Not because some external authority values it, but because we value it, and we're the only judges available. If consciousness is common, if billions of worlds host thinking beings, then our individual survival matters less to the cosmic story. But it still matters to us, to the particular instance of awareness that exists here and now. Either way, the search continues. Rovers drill into Martian soil. Probes fly through the plumes of icy moons. Telescopes scan distant atmospheres. Scientists analyze data, refine hypotheses, design better instruments. Each mission adds information, narrows possibilities, brings us incrementally closer to answering questions that might not have answers we like. Maybe we find life everywhere we look. Simple, persistent, unremarkable. The universe teeming with microbes that never evolve past basic cellular organization. That would tell us life is easy but complexity is hard. That the gulf between chemistry and biology is narrow, but the gulf between microbes and intelligence is vast. Maybe we find nothing. Decades of searching, increasingly sophisticated instruments, samples from dozens of worlds, all sterile. Earth alone, life a statistical fluke, consciousness an accident that happened once. That would tell us we're precious beyond measure, the universe's only attempt at self-understanding. Maybe we find something we don't expect. Life based on different chemistry, using different solvents, storing information in molecules we haven't considered. That would expand our understanding of what's possible, show us that biology isn't limited to the one example we know. Any of these outcomes changes everything. Not immediately, not in ways that affect daily existence for most people. But fundamentally, philosophically, in how we conceptualize ourselves and our significance. The wait continues. Missions are years in planning, years in transit, months or years analyzing results. Science operates on timescales that don't align with human patience. We want immediate answers to questions that require decades of careful work. But some questions are worth the wait. Some knowledge is worth pursuing even when acquisition is slow and expensive and uncertain. The search for life beyond Earth is that kind of question. Fundamental enough to justify the investment, profound enough to change everything if answered. So we keep looking. Building better instruments, sending more sophisticated probes, analyzing data with increasing precision. Each generation of scientists adding to the work of previous generations, standing on accumulated knowledge, pushing the boundary of what's known slightly further outward. And maybe, eventually, we'll know. Not through dramatic revelation but through accumulated evidence that finally crosses the threshold from possibility to certainty. A moment when the data becomes undeniable, when all reasonable doubt evaporates, when we can say with confidence that yes, life exists beyond Earth. Or no, we're alone after all. Both answers transform us. Both force reconsideration of assumptions we didn't know we were making. Both open new questions even as they resolve old ones. That's how knowledge works. Each answer generates more questions. Each discovery reveals new mysteries. We're not approaching some final understanding where all questions get resolved. We're expanding the boundary between known and unknown, and the boundary's circumference grows faster than its area. The universe is larger and stranger than we imagine. Probably larger and stranger than we can imagine. Our brains evolved to handle problems at human scales, understanding objects we can see and touch, timescales we can experience. Cosmic questions push against those cognitive limits. But we keep pushing anyway. Because that's what consciousness does. It reaches beyond itself, grasps for understanding that might be perpetually just out of reach. And sometimes, occasionally, it succeeds. Sometimes the universe yields its secrets, reveals its patterns, shows us something true. The search for life is that kind of reaching. An attempt to understand our context, our cosmic neighborhood, whether we share this vast space with others. And whether we find life or find ourselves alone, either answer is worth knowing. So that's where we are. Standing at the edge of something that could redefine everything we thought we knew about our place in existence. Ganymede's ocean isn't speculation anymore. It's confirmed. Real liquid water, vast beyond comprehension, sitting beneath ice in the darkness of space. And we're close enough to reach it, smart enough to design missions that could actually get there, curious enough to keep pushing even when the timeline stretches across decades. The answer might come from Ganymede, or Europa, or Enceladus, or from some unexpected corner of the solar system we haven't looked at carefully enough. It might not come at all, at least not in our lifetimes. But the searching itself matters. The fact that we're capable of asking these questions, of building the tools to investigate them, of dedicating resources and careers to understanding whether we're alone. Every mission teaches us something. Every dataset narrows the possibilities. Every failure informs the next attempt. We're not stumbling blindly anymore. We're methodically eliminating uncertainty, building toward conclusions that will stand regardless of what we want them to be. And maybe that's the real story here. Not whether life exists on Ganymede, but that we've become the kind of species that can find out. That we've developed the technology, the knowledge, the sheer stubborn determination to send machines across hundreds of millions of kilometers and ask questions about oceans we'll never see directly. The universe doesn't owe us answers. It doesn't care about our curiosity or our need to understand. But it's revealing itself anyway, piece by careful piece, to minds capable of interpreting the evidence. We're part of the cosmos trying to understand itself. And sometimes, when we look hard enough and think carefully enough, understanding happens. Ganymede waits beneath its ice. Silent. Patient. Holding secrets that might transform us. The search continues because we are parts of the universe trying to understand itself. Piece by careful piece, the universe reveals itself to minds capable of interpreting evidence. The answer is waiting. And soon, through our courage and science, we will know.